Data science is revolutionizing our world at a rapid pace, with the global market projected to reach $189.1 billion by 2024 and demand for skilled professionals growing 36% annually. Every day, we create an astounding 2.5 quintillion bytes of data. This explosion of information is transforming industries from healthcare to finance, creating exciting new opportunities. The dramatic, futuristic visualization on this slide represents the power and complexity of big data analysis, with glowing connections and nodes symbolizing the interconnected nature of this data revolution. The bold, high-tech color palette of blues and purples sets the tone for the transformative impact of data science on our world. Data science is an interdisciplinary field that combines statistics, computer science, and domain expertise to extract valuable insights from data. It employs rigorous scientific approaches, algorithms, and systems to analyze complex information. Data scientists build models that discover patterns and predict future outcomes with remarkable accuracy. Data science has the power to uncover hidden insights and make accurate predictions that can drive business success. The key is bringing together the right mix of skills: quantitative analysis, programming, and subject matter expertise. The data science workflow is a structured approach to solving complex problems using data. It consists of 5 key steps: problem formulation, define the problem and generate testable hypotheses; data collection, gather relevant data from diverse sources; data cleaning, process and prepare the data for analysis; exploration, perform exploratory data analysis to understand patterns in the data; modeling and deployment, build, evaluate, and implement data-driven solutions. Data science is a multifaceted field, and there are several key skills that are crucial for success. Business acumen is essential. Being able to translate data insights into tangible business value is a critical skill. Data visualization is key for communicating findings effectively to both technical and non-technical stakeholders. Machine learning expertise is vital for building predictive models that drive business impact. Strong statistical analysis skills, including understanding probability and inference, are foundational. Proficiency in programming languages like Python, R, and SQL is a must-have for data scientists. Structured data like databases, spreadsheets, and CSV files make up around 15% of all data. Unstructured data like text documents, images, and videos make up around 80% of all data. Semi-structured data like JSON, XML, and email make up around 5% of all data. Other data types include time series, spatial, and network data. These different types of data require different tools and techniques to manage and analyze them effectively. Understanding the characteristics of each data type is crucial for designing robust data management and analytics strategies. Surveys and questionnaires allow us to directly collect data from targeted participants, providing structured insights with an average response rate of 35%. Web scraping is an automated method of extracting data from websites, though over half of sites implement anti-scraping measures to protect their content. APIs and databases offer structured access to existing data repositories, making them efficient for regular data updates and integration. IoT sensors connected to 14.4 billion devices can capture real-time physical world metrics continuously. Each of these data collection methods has its own strengths and trade-offs that we'll need to consider when designing our data strategy. Data quality issues are a common challenge for data scientists and analysts. Real-world datasets often contain a significant amount of missing values, around 15–20%. These gaps can complicate analysis and modeling efforts. Outliers and anomalies in the data can also skew results. While they may represent errors, they could also highlight important edge cases that shouldn't be ignored. Inconsistent data formats, such as varying units or date formats, create integration problems. Standardizing the data is essential for effective analysis. Duplicate records can inflate metrics and create false patterns in the analysis results. Identifying and removing these duplicates is an important data cleaning step. Data preprocessing is a critical step in any machine learning or data analysis project. Feature engineering involves creating new variables that better capture the underlying patterns in the data. Normalization is important to scale variables to comparable ranges, so that no single feature dominates the model. Dimensionality reduction techniques like PCA can help explain 85% of the variance in the data using fewer dimensions. Data cleaning is essential to handle missing values, outliers, and inconsistencies in the dataset. Exploratory data analysis is a crucial step in the data science process, where we closely examine the data to uncover insights and patterns. The key steps in EDA include univariate analysis, looking at the distribution and statistics of individual variables to understand their characteristics. Bivariate analysis, studying the relationships between pairs of variables, calculating correlations, and identifying patterns. Multivariate analysis, analyzing the complex interactions between multiple variables to uncover hidden dependencies. Statistical testing, applying formal statistical tests to verify hypotheses, calculate p-values, and determine confidence intervals. Data visualization is a powerful tool for communicating insights and telling a compelling data story. Today we'll cover 4 key best practices to create effective, engaging data visualizations. First, it's important to choose the right chart type to match your data and the story you want to tell. Bar charts are great for comparing values, while line charts excel at showing trends over time. Next, consider color theory and accessibility. 8% of men have some form of color blindness, so use color strategically to enhance understanding. Eliminate unnecessary chart junk, remove any decorative elements that don't directly add informational value. Finally, incorporate interactive elements when possible to increase engagement and allow viewers to explore the data from different perspectives. Statistical foundations are the core principles and techniques that underpin data analysis and decision-making. This slide provides an overview of the key statistical approaches and their common applications. Descriptive statistics focus on summarizing and describing data, using measures like mean, median, and variance. Inferential statistics involve hypothesis testing and p-values to make inferences about populations from sample data. Bayesian statistics incorporate prior beliefs and update them with new evidence to arrive at posterior probabilities, useful for tasks like spam filtering. Regression analysis models relationships between variables, with linear, multiple, and logistic regression being common techniques. Time series analysis methods like ARIMA and PROFIT are used to forecast future values based on historical patterns, important for financial forecasting. Machine learning is a powerful set of techniques that allow computers to learn from data and make predictions or decisions without being explicitly programmed. There are 3 main types of machine learning: supervised, unsupervised, and reinforcement learning. Supervised learning is the most common, where models are trained on labeled example data to make predictions on new, unseen data. This makes up about 70% of real-world ML applications. Unsupervised learning is used to find patterns and structure in unlabeled data, without any specific target. This is useful for clustering and dimensionality reduction. Reinforcement learning is where agents learn through trial and error interactions with an environment, aiming to maximize some reward signal. This powers many autonomous systems. All 3 of these paradigms have unique strengths and are used in a wide variety of real-world applications. Popular machine learning algorithms are widely used across various domains, each with its own strengths and performance characteristics. Linear regression is a classic algorithm that provides a good baseline, with typical R-squared performance around 0.8 in real-world applications. Random forests are powerful ensemble models that excel in medical diagnostics, achieving up to 92% accuracy in some studies. Gradient boosting is another highly effective algorithm, winning many Kaggle competitions with performance around 60%. These 3 algorithms represent a diverse set of machine learning techniques that data scientists can leverage depending on the specific problem and dataset. The visualizations on this slide provide a helpful comparison of the technical attributes and performance of these popular algorithms. Neural networks are the basic building blocks of deep learning, inspired by the structure and function of the human brain. Convolutional neural networks are a type of neural network that excel at image recognition tasks, achieving 99% accuracy in many benchmarks. Recurrent neural networks are designed to process sequential data, like text or speech, and maintain a memory to understand context. Transformer models, like BERT and GPT, are a powerful type of recurrent network that have revolutionized natural language processing. Natural language processing, NLP, is a field of artificial intelligence that enables machines to understand and process human language. NLP powers a wide range of applications, from sentiment analysis of customer feedback to language translation. The slide shows several key NLP concepts and techniques, including tokenization, sentiment analysis, entity recognition, and language translation. Modern NLP systems can achieve up to 85% accuracy in sentiment analysis, which is critical for understanding customer opinions and feedback. The visualizations on the slide help illustrate how NLP systems work, from pre-processing raw text to extracting meaningful insights. NLP is a rapidly evolving field with many exciting applications, and is a key component of building truly intelligent and human-centric AI systems. Computer vision is a rapidly advancing field with many exciting real-world applications. In medical imaging, AI systems can detect anomalies with 98% accuracy, identifying issues that human radiologists may miss. Object detection using YOLO can process 45 frames per second, enabling real-time analysis of video streams. Facial recognition with deep learning achieves 99.97% accuracy, with applications in security and personalization. Video analysis can track motion and behavior patterns, providing valuable insights for surveillance and sports analytics. These are just a few examples of how computer vision is transforming industries and solving complex problems. Big data technologies have revolutionized the speed and scale of data processing. Traditional databases can only process data at a baseline speed of 1. Hadoop can process data 10 times faster than traditional databases. Spark can process data 100 times faster than traditional databases. GPU computing can process data 1,000 times faster than traditional databases. These dramatic improvements in processing speed enable us to tackle much larger and more complex data sets. The choice of technology depends on the specific needs and requirements of the project. Data pipelines come in two main types: ETL, extract, transform, load, and ELT, extract, load, transform. ETL processes data before loading it into a data store, while ELT loads the raw data first and then transforms it. The choice between ETL and ELT depends on factors like data volume and processing needs. Data can be stored in data lakes, raw, unprocessed, or data warehouses, structured, optimized. Modern data platforms like Snowflake, Redshift, and BigQuery provide robust data storage and processing capabilities. Stream processing is critical for applications that require immediate insights from real-time data. Key stream processing tools include Kafka and Flink. Classification metrics provide a comprehensive way to evaluate the performance of a machine learning model. Accuracy measures the overall correctness of the model's predictions. Precision shows the reliability of the model's positive predictions. Recall captures the model's ability to find all the positive instances. The F1 score balances precision and recall, giving a more holistic view of the model's performance. Regression metrics are used to evaluate the performance of models that predict continuous values. Mean squared error, MSE, penalizes larger errors, while root MSE provides the error in the original units. Mean absolute error, MAE, is more robust to outliers than MSE. R-squared indicates the percentage of variance in the target variable that the model can explain. Validation techniques like k-fold cross-validation and A/B testing help ensure the model's performance generalizes well. ROC curves provide a visual way to assess a classification model's performance across different decision thresholds. Data science has significant ethical implications that must be carefully considered. Bias and fairness are critical issues. Algorithms can perpetuate societal biases, so fairness measures must be built into the development process. Privacy is a major concern, especially with regulations like GDPR that impose heavy fines for violations. Privacy-preserving techniques are essential. Transparency is increasingly important as well. Black box models raise ethical questions, so explainability is crucial. These three areas, bias, privacy, and transparency, are key ethical considerations in data science that must be proactively addressed. Data science is transforming healthcare in powerful ways. Early disease prediction using AI can identify patterns that precede symptoms, enabling 94% accuracy in early diagnosis. Machine learning is accelerating drug discovery, reducing development time by 50% through more efficient compound screening. Personalized medicine tailors treatments to individual genomic profiles, accounting for unique variations to inform therapeutic decisions. Data-driven optimization of healthcare operations can reduce wait times by 35% and improve resource allocation in facilities. Data science is transforming the finance industry in several key areas. First, in fraud prevention, AI-powered detection systems are saving companies over $14 billion annually by catching fraudulent transactions. Second, algorithmic trading now accounts for 70% of all U.S. equity trading volume, using advanced data models to make rapid, high-volume trades. And third, data-driven credit scoring models are achieving 85% accuracy in assessing risk, enabling more efficient and reliable lending decisions. These are just a few examples of how data science is driving innovation and optimization across the financial sector. Data science is transforming marketing in powerful ways. One key application is customer segmentation, dividing the market into distinct, targetable groups. This allows us to better understand our customers and tailor our offerings to their unique needs and preferences. Another powerful use is personalization, using data to customize content and experiences for each individual. Recommendation systems are a great example. They drive 35% of Amazon's sales by suggesting products customers are likely to want. Data science can also help predict customer churn, which is critical in industries like telecom, where we see 85% accuracy in predicting who is likely to leave. Data science is transforming manufacturing operations across key areas like predictive maintenance, quality control, supply chain optimization, and digital twins. Predictive maintenance uses sensor data and algorithms to detect potential equipment failures before they happen, reducing unplanned downtime by up to 45%. Computer vision and AI-powered quality control can identify defects with 99.7% accuracy, far surpassing human inspection capabilities. Supply chain forecasting models predict demand patterns with precision, enabling a 25% reduction in inventory costs. Digital twins, virtual replicas of physical systems, allow manufacturers to simulate performance and test new designs without the need for physical prototypes. These data-driven innovations are driving major efficiency gains and quality improvements across the manufacturing industry. Deployment strategies are the methods we use to move our machine learning models from development into production. Containerization with tools like Docker and Kubernetes allows us to package our models and dependencies into scalable, portable containers. MLOps refers to the CI/CD pipelines and processes we set up to automate the deployment and monitoring of our machine learning systems. Monitoring and maintenance are critical to detect model drift over time and ensure our production models continue to perform well. Data teams combine diverse roles and skills: data scientists, engineers, analysts, and business stakeholders. Each role contributes unique expertise to create value from data. Data scientists work with advanced analytics and visualizations. Data engineers build the underlying data infrastructure and pipelines. Data analysts create reports and dashboards for business users. Business stakeholders provide domain expertise and data needs. Collaboration across these roles is key to successful data initiatives. The current challenges in data science that we'll cover today are explainable AI, data privacy, model fairness, and legacy integration. Explainable AI is crucial for adoption in regulated industries, and techniques like LIME, SHAP values, and rule extraction can help address this. Data privacy is a major concern due to GDPR and CCPA compliance, but approaches like differential privacy and federated learning can help. Model fairness is important to avoid perpetuating societal biases, and fairness metrics along with bias mitigation algorithms can mitigate this. Legacy integration is a challenge that slows down implementation timelines, but API layers and microservices architecture can help overcome this. AutoML platforms can reduce model development time by up to 60% and make machine learning more accessible to non-experts. Low-code and no-code visual interfaces, empowering business users to create their own simple data science models without technical expertise. Edge computing allows data to be processed where it's generated, reducing latency and bandwidth requirements. Quantum machine learning has the potential to solve complex problems exponentially faster, though it's still in the early research phase. The future of data science is an exciting and rapidly evolving field, with several key areas that are shaping the way we approach data and decision-making. Causal inference is a critical advancement, allowing us to move beyond simple correlations and truly understand the underlying causes behind the phenomena we observe. This enables more reliable and impactful interventions. Multimodal learning systems that integrate text, images, audio, and other modalities are creating a more human-like understanding of the world. This can lead to more natural and effective interactions with technology. The collaboration between humans and AI is a powerful framework that leverages the unique strengths of both. By combining human insights and creativity with the processing power and pattern recognition of AI, we can tackle complex problems in new and innovative ways. These areas represent just a glimpse of the transformative potential of data science in the years to come. As we continue to push the boundaries of what's possible, the future holds great promise for data-driven decision-making and problem-solving. Data science is a powerful force that is transforming every industry, driving $15.7 trillion in global economic value. Success in data science requires an interdisciplinary approach, combining statistics, computing, and deep domain knowledge. No single discipline on its own is sufficient. Responsible AI principles are non-negotiable. Ethics must be built into data science solutions, not just bolted on as an afterthought. The field of data science is evolving rapidly, so continuous learning is essential. Technical skills and human skills like communication and problem-solving are both crucial for long-term success.